question at the end, maybe. So our next speaker is Catalina Alvarado-Rojas from Colombia. I don't know how to pronounce your university, so you might want to do that. All right, thanks.
So good afternoon, everybody. You'll listen to me. It's okay? Yeah? Well, I will talk to you about introduction to seizure prediction. It will be a very general talk. So let's start. In fact, why do we talk about prediction? Because we want to infer, or we want to conclude something about a system that in our case will be the epileptic brain from some observations that we have, from some data. So we will start with a question. We need to start with a clear question, a precise question for a prediction algorithm. Not necessarily for seizure prediction, but in general terms, we need a question that we would like to answer at the end. So for this question, we need some data. This data need to be a good quality data, need to be the closest data to the question that we want to answer. We usually need, like, the more data that we have, the better. So this is a very important part, the observation or the measures that we are taking from the system. Once we have the data or the observation or this raw material, we can use it directly, or we can also extract some features. We usually have a lot of data. We want to take from this data the relevant information. We want to reject the redundant information. So it is a very good idea to extract some features from this data. We will talk a little bit about what kind of features can we extract, how can we classify them. And indeed, like the feature extraction, it is a very important step on the seizure prediction algorithm. So let's think about it. Once we have the features, we will use them as the input data to the prediction algorithm. The prediction algorithm is the core, let's say, of the seizure, of the prediction, not necessarily seizure, but of the prediction. However, it is like there exist like different algorithms, since the simple threshold to more sophisticated nonlinear algorithms, and even if it's like the core, you can, like, if the features, if the data is good, it's good, and the features are also a good selection, probably the algorithm will work. They will work very similar. So the two steps of the data acquisitioners and feature extraction are probably much more relevant when you are talking about prediction. And for the algorithm, we usually need some parameters. Those parameters are very important too. They will allow us to have different performance of the algorithm. When we want to implement the algorithm and select some parameters, we will have to split our data in two different sets. The training set is precisely to determine those parameters of the algorithm, and the testing set that will allow us to evaluate the method. So the evaluation is the next step of the seizure of the prediction, and once we have the parameters defined during the training set, we will use those parameters to evaluate the performance of our method. And then finally, if we have the performance, we have the method implemented and the evaluation of this method, we will have, let's say, we will have some conclusions about our question, and hopefully we will have an answer to our question. It's not yet the case, probably, to seizure prediction, but we are working on that. So what do we expect from a predictor, or what do we expect from the prediction? We want our predictor or our prediction to be interpretable. So we want that if we have a prediction method or a prediction algorithm that works, we want to be able to interpret the results. This is even difficult sometimes in seizure prediction, let's say, because we want to know something about our biological system. It's not necessarily the case with very sophisticated prediction methods. So we have to take into account that at the end we want to interpret the results of our prediction method. We also want our predictor to be simple and also to be fast. Why? Because we want it to be implemented probably in real time. We want to be implemented in a portable device or a small device, so we want it to be simple to implement, and we want a good speed of processing. We don't want to wait. We would like, for sure, we will have a lot of data, huge amounts of data to analyze, so we want the processing, the computer processing to be lower, to be easy. Then we also need our prediction to be scalable. What's that? So we usually will design or implement our prediction algorithm, and we would like to, we will have just a data set, a small data set. We will implement the predictor, and then we will probably want to implement it for ambulatory use. So we want the predictor to work in a small data set, as well as in a huge or in a longer data set. So we want to change and work for all the data that we have. And all those features, all those characteristics important for a predictor or during the prediction will be trade-offs of the accuracy, that it's kind of the most important, or how we will evaluate our predictor. So the performance of the predictor is usually measured with the accuracy in terms of sensitivity, specificity, and so on. So those four first characteristics will be usually trade-offs with accuracy of the method. Okay, so it was kind of a general view of a predictor, but let's talk about our concern here in this workshop, that it's the epileptic seizure prediction. So let's talk about the question that we have here in this workshop. So we all know that an epileptic patient will present recurrent and spontaneous epileptic seizures due to the abnormal electrical activity of the brain. These seizures will be represented by an abnormal behavior of the patient, but also by the abnormal epileptiform activity of the brain. So here we have patient with its electrical activity. At a point we will have the seizure. It's reflected in the behavior and also in the EEG activity. So because they are spontaneous, the seizures will limit a lot the quality of life of patients. But what if we can design or implement a method that will be able to detect this period just before the seizure onset? So if we we have the interictal period, that is between seizures, then the ictal period, that is the seizure. What if we can detect the preictal period? Some people also call it with differences, proictal, but then our question will be if we can identify the time when the seizure will probably occur without a priori knowledge of the onset time. If we don't know the onset time, but we can detect something just before that will tell us when the seizure will occur. So obviously, this is not a new question. We have a brief story here. Like more than 15 years ago, the seizures were believed to begin abruptly. But then some patients usually have some subjective feelings. They could be just at the beginning of the seizure, just some seconds before, what is known as auras. And then the patients report that these subjects' feelings could be some hours before the seizure occurs. So what it's called prodromes. These two, especially the prodromes, have been evaluated in a statistical way, in a more formal way, and they could be very, very subjective to patients. So they would feel that they have the prodrome after the seizure occurred, and it could be biased. So it's probably not very confident, a very confident characteristic. Then, so it was more than 50 years ago. Then, around 1970, it was Biglioni who first think about seizure prediction from the EEG, like extracting or recognizing some patterns in the EEG and then some precursors, and then use them to predict seizures. So he has a couple of works of papers of that time, but it gave the scientific community the idea of seizure prediction. So it was between the 80s and the 90s that many seizure prediction methods appeared. First, like very basic linear, evaluating the spike rate, much more basic, but then with the advent of nonlinear methods, with the improvement of technology, because the very first studies were very limited in terms of computing. So with the improvement of technology, like groups were able to evaluate much more methods and to improve the seizure prediction. They were very optimistic, actually, at the beginning. The studies, they will show that that predictor changes were easily identified in the EEG. However, they were not properly, let's say, evaluated. So at the beginning, it was a lot of exploration, and in fact, it needed maybe some time to start defining the real rules or a framework to evaluate those methods. So at the beginning, we have a lot of methods, very optimistic, but then when we start realizing that it needed statistical validation, it needed longer periods of time, then it was less optimistic, let's say. With that, then, as I told you, like a framework for seizure prediction was established in the last years, and now we know that we need long-term continuous recordings for a predictor to be useful or to be feasible, we need to do prospective analysis, for sure. We will talk about it later. And then we still are improving our technical and methodological strategies. So we are still working a lot on methods, new features, and then we also are still improving the data. Why the data? Because it has been during the last years that we have, for example, the microelectrodes. So we are exploring all that and probing all that. We have a lot of work, but it's good. Okay, so we talked a little bit about the question. Let's talk now about the data. What type of data should we extract for a seizure prediction? So mostly, let's say most of the works until here have been are based on EEG. The EEG has been like the gold standard. Think that why? Because we can't see the seizures on the EEG. So probably we could see also the precursors on the EEG. We explored, or many studies have explored surface EEG and intracranial EEG, especially microelectrodes. But as I told you, recently we are able to explore also with the microelectrodes much more focal activity of the brain. So this is maybe opening a new field in seizure prediction or a new field of exploration. However, there are other measures, such as blood flow and heart rate. For example, I have some reference here. We don't know. Maybe we have much more data to explore still with new techniques that we maybe don't even know. So for instance, we have the EEG mostly, but then we have to continue to improve that. And then what more about the data? We have to think about the quantity of data. We need a good amount, usually. Why? Because we need to split our data in the training and testing set during the algorithm design and implementation. We also need to have a condition, and we need to have a control. So the condition will be the predictable periods that we want to classify and to detect, and then the control has been widely used, the interictal segments. So especially for intracranial EEG, we won't have a lot of voluntaries with no non-epileptic voluntaries. So we really needed a control that we can use always, and this is the interictal period. And this is what the two things that we will classify or discriminate. Then we have also to think about the properties of data, because EEG data is completely non-stationary, and it makes us think, take a different approach to analyze this data, and it's usually the window analysis. So we also would like to have a good quantity of data to do a sliding window and then to analyze our continuous data. So these are some concerns about the data, but what they are talking to us is that we really need lots of data. We need a good amount of data, and this is probably what happened before. So first studies were limited on that. Right now, we are working hard on that, and I will show you now why. Because we are working on EEG databases. So the first databases were worked locally at some universities. We have the University of Michigan, Bonn, Boston, Lawrence, Freiburg has done a lot of effort on the Freiburg database at the beginning. They contain EEG data, usually small segments, sometimes 1 day, but then probably still not enough for seizure prediction, for what we think about when we talk about continuous long-term recordings. So more recently, there was the Epilepsy project. I worked on that also. We were four members from Germany, France, Italy, and Portugal, and we construct the Epilepsy database. It contains 275 long-term recordings, so about more than 3 or more than 4 days, with 217 scalp datasets and then 58 intracranial recordings from patients. This database is annotated by the experts, by the medical doctors, epileptologists, and it contains also some additional data about the patients, type of epilepsy, type of seizures, drug administration, and some other important information that will always enrich the method. Then there is also another initiative that is the IEG portal. It contains a lot of data sets, like 1,200, around from animal and human data, epileptic data. And I think that, well, you will listen to them later on this workshop. Okay, so with all this data, we want to extract the features. But then sometimes, and it's very useful to first start by pre-processing the data. What can we do to improve this data before extracting the features? So we can select visually some channels, and then there are some channels that are usually very noisy, so we want to extract them. We also can extract the artifacts, for example, directly, visually or automatically. We can also select some segments that we prefer for for the good behavior of our method. And we can smooth, for example, we can filter the data just before start extracting the features. So we can do several time. 1 second.
In the three-dimensional figures, what do you
call
the axis?
Now, just lines. So they are just features. Yeah. There are some lines, but there are no axis names.
No, I don't see
No, yeah, it's just the line. Those are just features. Whatever. No, there is no any feature that we have. And then we can extract, so here we start talking about the feature types. We can extract features from one channel, single channels, what we call univariate features. And this is, for example, so they are transformation of the raw data. And we will have here, for example, the feature space, let's say, the feature axis. And then we have some points. So it could be like a small segment of the raw data will reflect or will be transformed in a point, for example, or in a group of points in the feature. So extracting some features. They can be linear or they can be non-linear. So linear will reflect will be a linear transformation. points, then we can also think that this is a nonlinear system, and we will have a transformation to a phase space. And we will talk about, think about it, trajectories, and so on. So from univariate features, we can do linear or nonlinear transformations, and then for if we take the relationship between different channels, we can also extract linear and nonlinear features, as is shown here. Those are just very representative examples. There is no feature at all, let's say, but then we have here. And at the end, what we can also do is a dimensionality reduction. So we have probably, if we have a lot of channels, if we have all the relationships between channels, we will have a lot of data, still a lot of data. So we can transform those features to another space. This is, for example, what is done in principal component analysis, PCI, and then we will just choose the features that will be much more, that will have much more variance between them than those that are very similar between them, or between all the points that we have. So at the end, we can only select some of the data, some of the features, and then reject the others. And we have a lot of, with this in mind, we have a lot of methods that have been proposed. Here I give a very, very general mapping of the methods that we have. So we have univariate and multivariate methods. We have linear and non-linear methods. And I give you some examples of works that have used one or the other for seizure prediction. So you can, for this, you can, for example, extract from univariate, from single channels, you can extract the real power using Fourier transform, using Weber transform, and that are linear operations, and use that or some measures of that at the end, for example, the wavelet entropy, to detect predictor periods. You can also use accumulated energy. You can also model your signal as a linear model, and then use autoregressive models for that. Some statistical moments you can use. So my work that will be presented tomorrow, I use cross-frequency coupling. That is the interaction between different frequency bands for a single channel. And then you can use also nonlinear methods as the correlation dimension, Lyapunov exponent, and the similarity index. All those are methods that have been applied to univariate data, so to single channels, but that have also the analogy in the multivariate data. For example, you have also autoregressive multi-channel models, or also Lyapunov exponent for multi-channel, some measures. Then also you can extract phase synchronization. So synchronization and correlation will be widely used to relate or to extract the relationship between a couple of channels when we are talking about multivariate. So first, the methods were based more on relationships between two, so bivariate, but then some others have been developed to evaluate multiple channels at the same time. And so with these features, we would like to discriminate preictal and interictal period. I am not going very deep into that because there was this morning a talk about machine learning, but what we usually do is, well, we can use a threshold crossing, so all the features that are over a certain threshold or a certain value will be classified as one class, then below this value will be classified as the other group. So this is probably the simplest. But then there are also some classifiers that will learn from the data that you have during the training and then apply nonlinear classifications during the testing with some parameters that you will find. So you have support vector machines and artificial neural networks as examples, and because they have been the most widely used methods in seizure prediction. I can even say that support vector machines is kind of the most preferred method, or it has been evaluated a lot. Like that there are some works that have compared different classifiers, and then SVM ends to be one of the better, probably. The best, sorry, probably. So, yeah, so we have the algorithm, but then I talked to you that we have to choose the parameters of the algorithm, and this is usually done in the prospective study, where we have first our training dataset, then we have the testing dataset, and we will have this first part or this first segment to train the algorithm based on the performance of it. So we will try several parameters, several values for the parameters, and because we know for the training dataset, we know the result. We know if this is preictal or this is interictal. So with that in mind, we will try different values of the parameters, and then we will select the parameter that give us the best performance. This is for the training set, but then we have to, with these parameters that we already have, we will test the algorithm, and we will use the same parameters, and we will evaluate the performance with new data that the algorithm doesn't know, and that haven't been, the parameters haven't been optimized for that data. So what we want to avoid here is overfitting of the method, so that the method, if we have an algorithm, a prediction algorithm trained from some data, it could work very, very well from this data. But then if we have something new, maybe if it's not optimized, it won't work that well. It will, yeah, it will actually usually it won't work that well usually, but maybe it will work very, very bad, or maybe it will work comparable. So we have to make here good decisions. So how long do we want the training data set, or do we want it to split here, just one seizure here, one seizure there, like distributed in time for the training and for the testing too. So we have to do some decisions here. Yeah. What? I think that's it. Oh no. So what we can do if we have what is very used is to do cross-validation. That it's taking a small data set for training, then testing with the rest, then changing everything, then taking randomly another group for testing and another group for training and another group for testing, and doing that several times. Then that could help us to avoid this overfitting and improve our prospective, let's say, study. and give us like a much more real idea of the performance of the method. And finally, we have the evaluation, or the statistical validation of the method. So here I present, this is from Shelter, from your paper. We have here a segment of interictal and of preictal, raw data first, then a feature that has been extracted from it. It's just below for the interictal and for the preictal. And the line, well, the vertical line here in the preictal is the seizure, and the horizontal line in the extracted feature is the threshold. So it's just to cross the threshold, the decision if there is or not a preictal period. So once we have that, we have some alarms trigger those vertical lines with a zone or something, and then for the interictal period, we obviously we don't have any seizure coming, but then for the preictal period, we do. There is the seizure that is coming over there. So what is important here for the evaluation is several parameters that have been defined as a seizure prediction characteristic. And so is, for example, the first thing is the seizure prediction horizon. That is the time that we need for any control or action or intervention that we will take to prevent the seizure. For example, the minimum time that we need for a drug administration to act, or for the electrical stimulation. So this is the seizure prediction horizon. And then once we have done the intervention on the patient after the alarm, then we usually will have the seizure onset. The problem is that this is so stochastic that we will have not an instant for the seizure prediction, let's say onset, but then a small segment of time, what is called the seizure occurrence period. So it's the period where the seizure is thought to occur once the seizure prediction horizon has finished and the intervention has been done. So those two periods are important, and are important because they can help us to define the sensitivity of the method. That will be the number of seizures, of well-predicted seizures. So if a seizure occurred in the seizure occurrence period, it will be well predicted. So this is going to help. These periods will determine and define the sensitivity, and then the specificity. That is the ability of the method to, let's say, don't predict what it's not a seizure. For seizure prediction has been defined as the number of false predictions per unit of time. So sometimes we have, for other fields, before, specificity was more was defined more with the formal definition of the contingency matrix, and then one of the fields, the false predictions. But then here it's per unit time, not per event, let's say. And then with those two, with the sensitivity and the false prediction rate, we can evaluate the performance of our method statistically. But this is probably not enough. With this, we can compare methods, for example, but most importantly, and right now it's necessary to compare it to a random predictor. So why? Because we are testing so many variables, so many features, that we could predict something by chance. So what is established is that we have to compare our sensitivity values to a random predictor that will use the same false prediction rate or the same specificity that we have. And for that, and with that, we will have two critical values, one lower, one higher, that will tell us if we are above those values, those critical values, we will have a significant method. So this method of this random predictor will follow a Poisson process. Then we will have a binomial distribution of this. So P is the Poisson process that we have, that it's the probability for an event or for the predictor to trigger an alarm, just knowing that we have certain amount of or a certain value for the false prediction rate. Then we can detect with the combinatory here, we can detect as at least some like K, non-case or lowercase K seizures from uppercase K seizures in total that we have. And then if we take some significant value alpha, we will have a lower and an upper critical sensitivity. So what is the sensitivity that the random predictor will trigger at least some alarms well detected, and then so we have two because we have to take into account the number, the dimension of the features that we are using. If we were using only one parameter, it's not the case. We will have the critical sensitivity, the low sensitivity. If we are using a certain amount of features, like 13 channels or D channels, we will have a maximum value of critical sensitivity. The more features or parameters that we have in the method, the easier will be for the random predictor to by chance predict a seizure. So we will have to take that into account. If we have a higher number of parameters, it will be, let's say, worse for us, for our method, and better for the random predictor. We want to avoid that, so we want to limit the number of the parameters. And once we have validated our method, what we can think about it's a seizure prediction system. So something that will be implanted or will be portable, ambulatory for the patient, and that will warn here that a seizure is coming. So there is also some work on that. It's actually the work from Cook and his group, and they already developed, they already implanted some patients, they already tested the methods of a seizure prediction system. And there is also the Epilepsy project. It was a non-invasive system, and it also acquired the data, extract the features, and then classify or try to predict the seizures. So those two systems, let's say, have been the most important efforts on the implementation of a seizure prediction system. Okay, so just to finish, I just put some questions that we can think or we can discuss a little bit. Obviously, I have not the answer for that, because otherwise, if we have the answer, we won't do a workshop on seizure prediction. It's kind of the topic that we are interested. So there are still many questions about the seizure prediction. But we can think about the different steps that we have, and what we can do to improve the seizure prediction. So is our question precisely enough? Or we have to define already much more things? Are we looking at the right type of data, or we are missing some variables, chemical variables, or I don't know, something that we are not even able to record right now? How long the predictal period should be? This is a very important point in the prediction algorithm, and it will bias or change a lot the performance. So this is important. What are the best features to extract? How to improve the sensitivity and specificity of the methods. So this can be, there are some works combining methods, combining features. This is probably a little bit easier to talk about, to discuss. And well, once we have the method, so it's the method better than chance or not, this is very important. And still, like, is seizure prediction possible? Yeah, so we don't know. Okay, thank you.
So we've got time for one question while Greg sets up. Anyone got a question? Yeah, is that?
Yeah, what is the false alarm? It's not a false alarm. There could be seizures. There could be events that will get into seizures.
Yeah, like a predictor.
Oh, you don't have a...
100% sure that
Is that
has been identified.
I'll go and ring it. I'll go get something. I'll go get something.
So that's why I talk about predictal more than predictal period. Predictal will be, maybe a period that will belong to a seizure, but not necessarily. Predictal, by definition, will be always before the seizure. But yeah, you're right. It could be, a change, predictal change that doesn't necessarily have a seizure afterwards. Yeah.
So we've all, except for this experience, I think, where we've tried to develop a seizure prediction algorithm that some reviewers sometimes will say, but it's already been solved, right? And so leading into the next talk, I think, how do you think the Kaggle competition has done to sort of, bring about laying to rest the question of whether there is actually predictability or there is differences between critical data and where do you think? I mean, some of the competition, people were getting 80 or 80 to 90%.
Yeah, just a notebook.
Their ability to distinguish between neurophil. Greg, you're about to talk about this. Is that right?
No, I'm having some problems. Does anyone have an adapter for a power? Yeah.
I was going to ask you to critique the Kaggle competition and how you think it's played a role in.
Yeah, and there's a talk on the Kaggle competition. Awesome. Thank you.
You got to push hard.
Okay. Wow, really hard.
Yeah, the exact question was just...
How do you think the Kaggle competition has influenced the debate about whether seizures can be predicted?
You shouldn't have to push that hard.
Yeah. Well,
Yeah, one.
So, yeah, I think that the important point is to really reproduce that on much more patients. Maybe, I don't know if it's enough or not already.
You must be really strong, Pat.
He's really strong.
He is really strong.
Oh.
Okay.
I agree. It remains.
I'm in desperate need of a new computer. I apologize for the delay.